Okay, so imagine needing power in places where wires just,
Yeah.
well, they can't go. Think deep inside your own body, maybe for a medical device, or way down underwater for exploring the ocean.
Right, it's a huge challenge. How do you get reliable power to electronics in these really, really tricky spots?
Exactly. And, you know, you might think of the wireless charging for your phone. That usually uses electromagnetic induction, right? Or maybe radio waves.
Yeah, induction or RF. But the problem is they don't work so well over distances, especially through something like body tissue.
Ah, okay. So the efficiency drops way down.
Way down. And the range is super short. Plus, you can sometimes get electromagnetic interference, which isn't ideal, especially for medical implants.
So those standard methods have real limits here.
They do, but scientists have been exploring other options, and one that's looking really promising is ultrasound.
Ultrasound, like for medical scans.
Sort of, yeah. Same basic idea sound waves, just at frequencies way too high for us to hear. But the cool thing is, unlike those electromagnetic waves, ultrasound actually travels through tissue much, much better.
Oh, interesting. It doesn't get absorbed as much.
Exactly. Less absorption, better penetration. That makes it, well, a really interesting candidate for powering things inside the body or, in water.
Okay, so instead of magnetic fields, we're using sound waves we can't hear to beam power. That's quite a shift.
It really is. And that brings us right to what we're diving into today. There's this really fascinating new development from a research team over at KIST.
KIST, that's the Korea Institute of Science and Technology.
That's the one. They
Mhm.
worked with folks at Korea University, and what they've done is engineer a new kind of ultrasonic receiver. And crucially, it's biocompatible.
Biocompatible. Okay, so body-friendly. We've got some details on this research, right, and what it might mean.
Absolutely. That's the plan for this deep dive. We really want to dig into this new receiver tech, figure out what makes it such a big step up from current methods.
And explore where it could take us. Like, what possibilities does it open up? Medicine, underwater tech.
Precisely. Both of those, potentially.
All right, so let's talk about the team. You mentioned KIST and Korea University. The leads were Dr. Sung-hoon Her from KIST and Professor Hyun-Kail Song.
That's right. And their big achievement here is this ultrasonic receiver that's not just biocompatible, which is huge in itself.
Yeah, it means the body is less likely to reject it.
Exactly. But it's also flexible, and it still works properly even when it's bent.
Flexible. Okay, that sounds important. Why is flexibility such a big deal here?
Well, think about the human body. It's not static, right? Things move, tissues flex. Or underwater, you might have uneven surfaces. A stiff, rigid receiver, that's just not practical.
Right, it wouldn't conform well.
Not at all. So this flexibility, it tackles a really fundamental problem, makes the whole concept much more adaptable for use, inside living things.
And they've actually shown it working, not just in theory.
Yes. And this is key. They demonstrated wireless battery charging using these ultrasonic waves. That's a massive step. It proves the concept is practical.
Okay, charging a battery with sound waves.
Wow.
Now, efficiency is always the name of the game with wireless power, isn't it? How well does this thing actually convert that sound energy into electricity? Did they improve on that?
They did, significantly. Our sources say the power conversion efficiency is much better than traditional ultrasonic receivers.
How they manage that boost?
It really comes down to a couple of things. First, they used some advanced piezoelectric materials.
Piezoelectric. That's the effect where squeezing something generates electricity, or vice versa.
Exactly that. These materials convert mechanical stress, like the vibrations from ultrasound, directly into electrical energy. So they picked high-efficiency ones.
Okay, better materials. What else?
And then a really clever structural design for the receiver itself. It's designed specifically to capture those incoming ultrasound vibrations more effectively.
So better materials plus a smarter design equals more power out.
That's the idea. Better harvesting of the sound energy.
And the results? Do we have numbers?
We do. They reported transmitting 20 milliwatts of power over 3 centimeters underwater.
Okay, 20 milliwatts underwater. And through skin.
At the same depth, 3 centimeters, but through skin, they got 7 milliwatts.
Right. Now, 7 milliwatts, 20 milliwatts.
Mm-hmm.
Help me put that in context. Is that actually enough power to run anything useful?
Yeah, actually, for the kind of devices we're talking about, it really is. Think about low-power electronics. Many wearable health sensors, or even some implantable devices like certain neurostimulators, or maybe even pacemakers down the line, don't need huge amounts of power.
So 7 milliwatts could be enough for continuous operation.
For some devices, yes, enough to keep them running continuously or at least significantly extend battery life. The researchers actually showed this off visually.
Oh, yeah.
They used the wireless power transfer to light up a little LED shaped like the KIST logo.
Okay. A simple demo, but it makes the point.
Exactly. It shows, look, this isn't just maths on a page. It can actually power something real.
Okay, so the medical applications. This feels like where it could really make waves, so to speak. Can you sort of paint a picture for us? How could this change medicine?
Well, think about implantable devices. Pacemakers, neurostimulators for pain or other conditions. Right now, they run on batteries.
And those batteries eventually run out, which means more surgery to replace them.
Exactly. It's invasive, carries risks. Imagine if you could power those devices wirelessly, continuously, right through the skin. You potentially eliminate the need for those replacement surgeries altogether.
Wow. Okay. That would be huge for patients.
Huge. And think about wearable sensors, too. The ones constantly monitoring blood sugar, heart rate, whatever. This could mean longer operation, maybe no need to constantly take them off to recharge. Safer, more reliable data.
It really could be a paradigm shift, couldn't it? Moving away from implanted batteries for some of these low-power devices.
It really points in that direction. Safer, potentially more continuous power, less invasive procedures. It's very promising.
But you mentioned it's not just medicine. The sources talked about underwater uses, too.
Yeah, that's another really interesting angle. Think about underwater drones or long-term sensor networks monitoring ocean currents or marine life.
Powering those must be a nightmare. Batteries run out, cables are limiting.
Precisely. It's a major bottleneck. This ultrasonic approach could potentially allow for wireless recharging underwater, or maybe even continuous power from a nearby source.
So underwater robots could stay down longer, explore further.
That's the potential, yeah. It could really open up our ability to monitor and explore the oceans in a way that's difficult right now. Longer missions, more persistent monitoring.
And we actually have a quote from one of the researchers, Dr. Herr at KIST. What did he say?
He said, through this research, we have demonstrated that wireless power transmission technology using ultrasound can be applied practically.
Applied practically. That's the key phrase, isn't it? Moving beyond the lab bench.
Absolutely. It signals their confidence that this is workable technology, and, they're not stopping there.
Oh, what's next for them?
They're already planning the next steps, things like making the receivers even smaller, miniaturization.
Right. Crucial for implants.
Definitely. And, of course, looking towards commercialization. How do you actually get this tech into real-world products?
Makes sense. The whole path from research to reality.
Yep.
Now, for listeners who really want to get into the nitty-gritty, we do have the specifics on the publication.
We do. The paper title is a body-conformal ultrasound receiver for efficient and stable wireless power transfer in deep percutaneous charging.
And it was published in Advanced Materials.
That's right, March 26th, 2025. And if you want to find it, the DOI is 10.1002 Atnamapot to GRIL 202419264.
Okay, DOI 10.1002 ADEMA 202419264.
Good point. It was supported by the Ministry of Science and ICT in Korea through the KIST Institutional Program and also the National Research Foundation of Korea, specifically their Nanomaterial Technology Development Project.
Right. Important acknowledgments there. And you mentioned visuals earlier. Did KIST provide images?
They did. There's a conceptual image kind of showing how this receiver might fit into an implanted medical device, and also a block diagram breaking down the components.
Ah, okay. So that helps picture how it all fits together.
Definitely helps visualize the application.
So let's try and wrap this up. When you look at the whole picture, this development, this flexible, biocompatible, efficient, ultrasonic receiver, it really feels like more than just an incremental improvement.
I agree. It feels like a significant step forward for wireless power, especially in these really challenging areas. Inside the body, underwater, places where traditional methods just struggle.
And the key advantages are pretty clear, right? It's ultrasound, so it's friendlier to tissue.
Much gentler, yeah. And it works efficiently deeper down than the old methods.
Plus that flexibility, letting it conform to the body.
Exactly. It addresses some real fundamental limitations we've had for a long time.
So here's a final thought to chew on. If we can now use sound waves to power things efficiently, wirelessly, deep inside us, or deep in the ocean, what else could this unlock?
That's a great question.
Where else do we need power? Where wires just can't reach, or where current wireless methods fail? Could this fundamentally change how we power? Well, everything. Our interactions with tech, the world around us, maybe even the world inside us.
It's definitely technology that makes you think about possibilities that seemed like science fiction not too long ago. A very mind-blowing prospect indeed.